Hello. Today we're going to cover initial value problems. So we are in section 1.2 of our book. And initial value problems are these are differential equations with an x, y value given. That's it. It just gives us some information so that we can determine from the solution that has like a plus c in it, which is a family of solutions, we can figure out which particular one goes through the point we're given. And we'll do some examples that help us understand that. So these types of differential equations typically have time as the independent variable, although it could be something else, or t could be completely arbitrary, like have no meaning whatsoever. But if it is time and y is the dependent variable, then y is going to represent position, y prime is velocity, and so on. IVPs, or initial value problems, have initial conditions imposed on the dependent variable and or its derivatives. So we might see information that is about x and y, and x and y prime, right? So some information about where the solution goes through and some information about where its derivative goes through. So when we're talking about that interval of definition, that was something that we talked about in the previous section. When we talk about the interval of definition of a solution, we saw that we would have to consider the function as a simple function first, right? That was one of the things we did. And we would just find its domain the same way we would in algebra. But then we also had to consider the function as a solution to a differential equation and examine its derivatives. And then we had to figure out if we needed to restrict the domain more or if it was fine and it matched what we found for the simple function. But if we're given an initial value problem, then we have to consider the given initial value as a point on the plane, and we have to make sure that the initial value is contained in the chosen interval of definition. So the initial value has to be contained within the chosen interval of definition. And we're going to get right to working on some examples that go over that to help that stick for you. So in this example, we are told that y equals 1 over x squared plus c is a one-parameter family of solutions. So they already did the work. They solved a differential equation. It was the y prime plus 2xy squared equals 0. They already solved it. They found that the solution is y equals 1 over x squared plus c. You're not being told to find a solution here, okay? That is one thing that you have to get very clear. In chapter 1, we don't know how to solve differential equations, so there's no expectation there. And I say that because the directions typically say, find a solution. And you're like, oh, I guess I have to know how to solve these. No, you don't. They're saying find a solution. Y equals 1 over x squared plus c is a family of solutions. We want to find one of those. So we want to find a solution of the first order initial value problem consisting of this differential equation and the given initial condition. And then we want to give the largest interval I over which the solution is defined. So just a note is that is really talking about what I just said. The way the question's worded, it makes you think that you're supposed to solve the ODE even though we've not learned any techniques. I just found a typo. We've definitely earned the techniques, but we have not learned the techniques. So we're not being asked to do that. And I can't stress that enough in this chapter. Okay, so we're told that y of negative 2 is equal to 1/2. This right here, this is the initial value. It's a point on the graph. And we could read it like y of negative 2. Negative 2 is the x value. So I'll put that in. And y of negative 2 is 1/2. So 1/2 is the y value. So we want to find c so that y equals, 1 over x squared plus c goes through this point, -2 with 1/2. And so the best way to find that is to plug in the x value, plug in the y value, and solve for c. That's it. So we will plug in x equals -2 and y equals 1/2 to the solution, the given solution that we did not have to find, and solve for c. So when we do that, y is 1/2. That's equal to 1 over x is -2, so I'm going to square -2 and then plus c. So when I do this, I get 1/2 is equal to 1 over 4 plus c. If we think back to a long, long time ago, if we cross multiply, we can get things in the right position. So we get 4 plus c is equal to 2, which means c is equal to -2. And so the question said to find a solution of the first order IBP. A solution is y equals 1 over x squared, and then instead of plus c, I put in -2. So that's it. That's all we're being asked to do. Now, the second part's a little bit harder, okay? Looking at this problem, I want to separate this from everything. So my interval of definition, y equals 1 over x squared minus 2. I can see that my domain for y is such that x squared minus 2 cannot be 0, and that means that x cannot be plus or minus the square root of 2. If it is, then we've just divided by 0. Okay, so I found the domain restriction for y. The derivative of y is y prime is equal to, this would be a -2x over x squared minus 2 all squared. I'm doing that part in my head here right now, but remember, you can rewrite 1 over x squared minus 2 to be, in parentheses, x squared minus 2 raised to the -1 power, and then just remember your chain rule when you take the derivative. Okay, so that's my derivative, and it looks like there are no new domain restrictions. So this has the same restrictions. So the interval of, I should say the intervals of definition are all the values that are not equal to plus or minus square root of 2. So they're going to be from minus infinity to the negative square root of 2, union the negative square root of 2 to the positive square root of 2, union square root of 2 to infinity, with all parentheses on everything. And so we're supposed to figure out which one of these is the one, okay? It can be really helpful to graph. So I have a graph already set up here, and I've already put in y equals 1 over x squared plus c. And I have a little slider on here, and right now it's at c equals 1, so I'm going to move it to c equals -2. Whoops. And then the initial value that we're working with right now is the one where x is -2 and y is 1/2. And I can see, let me put a label on it. I can plot that point on there, and look, it's on the leftmost part of the graph, right? So it looks like the initial value applies to the part of the solution that is to the left of the square root of -2, or sorry, the negative square root of 2. And so this is the image that I want to keep in mind when I go to my notes. I can even just kind of draw myself a really rough sketch that has the negative square root of 2 on it and the positive square root of 2 on it, and then just kind of draw myself what I saw. And the -2 with 1/2 was right there. on that leftmost corner. So we want just the interval from negative infinity to negative square root of 2. So our answer is that the interval of definition for the IVP is negative infinity to negative square root of 2. Okay? All right, let's try another one. Okay? Let's try one where we have a different initial value and see like the whole process again. It's the exact same process. So in this next one, we have y of 1/2 is equal to negative 4. So that is telling me that x is 1/2, y is negative 4. So that's the point that I'm given. So I'm going to substitute these into y equals 1 over x squared plus c to find c. So I'm finding my parameter. All right, so y is negative 4. That's equal to 1 over, and now I have a 1/2 all squared plus c. And go ahead and rewrite that. I get negative 4 is equal to 1 over 1/4 plus c. Okay, if I cross multiply here, what I end up with is 1/4 plus c is equal to negative 1/4. And if I subtract the 1/4 over, then what's going to happen is I get that c is equal to a negative 1/2. Okay, so my solution is y equals 1 over x squared. Instead of plus c, I'll put in minus 1/2. Okay, so this is my solution, and I've got to come up with an interval of definition again, and it's the exact same process right here. So an interval of definition for y would be that x squared minus 1/2 cannot be 0. Otherwise, we'd be dividing by 0. That means x cannot be plus or minus 1 over the square root of 2. And if we take the derivative, and I'm going to simplify this, so interval of definition for y prime, and y prime is equal to, very similar derivative, we'll get a negative 2x over, in parentheses, x squared minus 1/2, all squared. The interval of definition for y prime, the only restrictions are the same as they were for y, so it's the same. But now we want the interval of definition for the IVP. Okay. Now, I want to go back up above where I wrote x is not equal to plus or minus 1 over the square root of 2. We could say the intervals are minus infinity to minus 1 over square root 2, union minus 1 over square root 2 to positive 1 over square root 2, union 1 over square root 2 to infinity. And so for the interval of definition for the IVP, we have to figure out which interval is the right one. So we'll go back to Desmos again, and I'm going to unselect that first initial value, and I need to change my c value. We got c as negative 1/2, so I need to go to negative 0.5. Graph looks very similar, just kind of squeezed in a little bit, shrunk horizontally, but now I have a different initial value. And it looks like that initial value is falling down below the x-axis in the middle portion of the graph. So that upside down parabola shape is where my initial value is going, is where my solution is going through the initial value. And so that means the middle interval is the interval of definition. And again, I can kind of draw a really rough sketch of this to see it, so that we just have it here in our work. We know that the problems were negative 1 over square root 2 and positive 1 over square root 2, and our graph looked kind of like this. We have the downward facing parabola, and on that downward facing parabola we had the initial value 1/2 with -4, which is maybe showing up down here, something like that. Okay, it doesn't need to be accurate. I'm not looking for accuracy in the picture. I'm just looking for it to guide me, and that's it. So now I know my interval of definition for the IVP is the middle interval, which is in parentheses -1 over square root 2 to +1 over square root 2. So that is the other thing that I would box up. We've got a solution and we have an interval of definition. Okay. In the next example, we have more than one parameter. This is the case where we have a 2-parameter family of solutions of a second order ODE that was y double prime minus y is equal to 0. And I brought this up in the last section where I said sometimes you're going to see more than one parameter and they won't be written as plus c and plus d. And this is exactly that. Here we have y equals c1 e to the x plus c2 e to the minus x. This is this has parameters c1 and c2. And again, we will find out how these show up. I cannot get a 1 to save my life. There we go. We will see how these show up when we learn how to solve differential equations. For now, we trust that they found the correct solution and we're just trying to figure out what C1 and C2 are, okay? Now, we're being asked to find a solution for the second order IVP. That means they found a solution, they found the solution, the family of solutions. We have to find which one satisfies y of 1 is equal to 0 and y prime of 1 is equal to e. So what I need to do is I've got my y, and it has parameters c1 and c2. I need y prime as well. Taking the derivative, remember c1 and c2 are constants. The derivative of e to the x is e to the x. So y prime is c1 e to the x. And then the derivative of e to the minus x is minus e to the minus x. So I get a minus c2 e to the minus x. Okay, so it also has the same parameters as y, which are c1 and c2. So first I'll deal with y of 1 is equal to 0 and see what that gives me. After that, I will deal with y prime of 1 is equal to e and see what that gives me. And I might have a system of 2 equations that I can use elimination or substitution to solve. So y of 1 equals 0. That means c1 e to the 1 plus c2 e to the minus 1 is equal to 0. And y prime of 1 is equal to e. I get c1 e to the 1 minus c2 e to the minus 1 is equal to e. Okay, so I have 2 equations, I have 2 unknowns. I am going to solve for, let's see, I will solve for, the unknowns are C1 and C2. Okay, so I'm going to solve for C1. Maybe I'll solve for C2. I'll solve for C2 in equation 1. We'll call this equation 1, this equation 2. If I solve for C2, then I'm going to move the C1 times E to the right-hand side. On the left-hand side, I'm going to rewrite it as C2 over E, since E to the minus 1 just means 1 over E. This is equal to C1 times E. Continuing to solve for C2, I get C2 is equal to C1 times E squared. Okay, I'm using the substitution method to solve for C1 and C2. I got C2 in terms of C1. Now I'm going to substitute that into my second equation and see if I can solve for something. All right, so if I substitute this in, then I get C1e minus C2 is now C1e squared times the e to the minus 1 that was already there, and this is equal to e. Okay. Simplifying, I have e squared times e to the minus 1, so I add the exponents. I get e to the 2 minus 1, which is just e. So I have c1e minus c1e is equal to e. Is that what I wanted? Something went wrong. Give me just a second to think about this. I see it. I lost a minus sign. Okay. Over here in equation 1, hold on, let me just erase all that. We can pretend it never happened. Okay. Over here, when I solve for C2 over E, it should have been equal to a minus C1E. And so then C2 is equal to a minus C1E squared. That's going to make a big difference. Okay. So I go ahead and substitute that in for C2. I get C1E minus, in parentheses, C2 is minus C1E squared. All of this times e to the minus 1 is equal to e. Okay, now we'll simplify the exponents for e and the double negative. This becomes C1e plus C1e is equal to e. Well, that looks like we've got 2C1e is equal to e. And dividing by the 2e, I get C1 is equal to 1/2. So I get a value for C1. I can then take that and plug it into my expression for C2. And then C2 will equal, replace the C1 with 1/2. I get a negative 1/2 e squared. So those are my parameters. And that means that y, our a solution, so I'll write that, a solution is y equals C1 e to the x will be 1/2 e to the x. C2 e to the minus x will be minus 1/2 e squared e to the minus x. We might rewrite this one more time just to combine the e squared and the e to the minus x to be 1/2 e to the x minus 1/2 e to the 2 minus x. And this is what they were after. And that's it. Okay. Next problem, or next topic, is going to be about existence and uniqueness. And this is kind of the theory side of things, and it gets a little weird. And we do have to talk about that whole partial derivative thing a little bit. It's not hard. It's one of those things, if you know, you know, and if you don't, it's really hard. So we're going to know, and it won't be hard. Okay. So before solving any differential equation in real life, you want to know that there actually is a solution. And that seems kind of silly. Like, well, how would I know there was a solution, right? Well, if you think about when we were solving, for example, quadratic equations, and we knew that the solution would end up being complex because the discriminant said so. We knew that if we only wanted real solutions, but we were going to get complex solutions, we would say there were no solutions, right? Well, and we could determine that before solving. Well, we can't necessarily find things in that way. We can't determine if a solution exists in the same way as it would for a quadratic, but there is a way for us to know that a solution exists. And furthermore, to know that it's actually a unique, like just one solution, okay? So before solving any differential equation, we kind of want to know if a solution even exists and whether it's unique or not. So these are the questions we have to ask, or we should be asking ourselves. The two questions about existence. Does the differential equation dy dx equals some function of x and y have any solutions? And then, do any of the solution curves actually pass through the initial value that's given? The uniqueness question is, when can we be certain that there is precisely one solution curve passing through the point that was given, the initial value, x naught, y naught? And it seems kind of hard to believe that we can answer these questions without ever having found a solution, but we have a theorem that says we can, and it tells us what to do to make that determination. And I will admit that I'm going to read it out loud, and I'm going to read my note because I feel like the theorem, it's it's highly theoretical in how it's written. It's very precise and mathematical, and it can be scary and very unfamiliar to read and not clear either. So we want to clear it up. The existence of a unique solution theorem says that we're going to let R be a rectangular region in the xy plane. So a rectangular region is just meaning x goes from some a to b and y goes from some c to d. And that we want that region to contain the point x naught, y naught. Remember, this is the initial value. And that initial value should be somewhere in the rectangular region. Now, if f of xy, note, f of xy is dy dx, okay? So we're going to define dy dx to be some function of f of xy. And del f, del y are continuous on the rectangle. Del f, del y, this del f, del y is telling us to find, so del f, del y is equal to the derivative, the partial derivative. So I'm going to use a del instead of a d. Doesn't change a whole lot though. The partial derivative with respect to y only of f of xy. What that means is we're just going to treat x like a constant. And that's sometimes kind of hard to do depending on the function, but we've got to like really hone in on y is the only variable we care about, okay? So first, we isolate dy dx and we define it as f of xy. Then we take that and we find the first partial derivative of it with respect to y. And we want to show that they are both continuous on some rectangular region. And if we can, then there will exist some small interval that contains, that's contained within the bounds of x, and a unique function that is our solution and is defined on the interval that is a solution of the initial value problem. Okay, so that's still really confusing probably. The note that I wrote was, what this theorem is saying is that you need to define f of xy to equal dy dx, and then calculate its partial derivative, del f, del y. Then determine where they are both continuous. That's going to be your interval of definition. If the initial value is in that interval, yay, we know we have the existence of a unique solution. Okay, so let's try this, okay? We're being asked to determine a region of the xy plane for which dy dx equals the square root of xy would have a unique solution whose graph passes through a point, just any given point in the region, okay? So first, define f of xy to be equal to dy dx. And since dy dx is already completely solved for, this is equal to the square root of xy. I'm going to go further and rewrite that as, in parentheses, xy to the 1/2 power. Okay. Now, just thinking about that function itself and x and y values, in the first quadrant, we know we have positive and positive for x and y. In the second quadrant, x is negative and y is positive. In the third quadrant, they're both negative. And in the fourth quadrant, we have x is positive. I almost wrote x. X is positive and y is negative, okay? Now, I'm just thinking about how the domain of this is such that the product of x and y has to always be greater than or equal to 0. Okay? And the only way that's going to happen is if both x and y are positive or both x and y are negative. So that's either in the third quadrant or in the first quadrant. Those are the only possible places. If we're in the second quadrant, then the product of x and y would be negative. So we have either x greater than 0 and y, I should say greater than or equal to 0 for both, or we have x less than or equal to 0 and y less than or equal to 0. Okay, so I'm just getting that out of the way, so I've done it. Now I need to calculate del f del y, which is going to be taking the partial derivative with respect to y of xy raised to the 1/2 power. Okay, so this is a chain rule because there's a power, and then we have to step inside and take the derivative with respect to y. So what happens is this becomes 1/2 times xy raised to the negative 1/2 times del y of xy. Right? Just applying the chain rule without actually taking the derivative of the inner function yet. So now I can see what I need to take the derivative of still. It's xy. Remember, if we're taking the derivative with respect to y, then x is just a constant. You could treat it like a 7. So for example, if it was a 7, then the derivative of 7y would be 7. Well, then that means that the derivative of xy would just be x. And it is. So this becomes 1/2 times xy to the negative 1/2 times x. And then I can simplify this even further. I've got x over 2 square root of xy. Okay, now this could simplify just a little bit more because I have an x on top and I have a square root of x on the bottom, and I have multiplication and division all throughout, no pluses, no minuses. And so I could simplify this to be 1/2 times square root of x over square root of y. Okay, and then in this case, what would end up being true might be more confounding, like harder to figure out. But what I can see for certain, the way this is written, is that both x and y need to be positive when it's written this way. Whereas if I leave it in the unsimplified form, and I'm doing this on purpose to show you how sometimes when we simplify, we lose information. So if I leave this in the unsimplified form, I can see here that, again, it's xy, the product of x and y, that must be greater than 0, not equal to 0 anymore, because the product of xy is in the denominator. Okay, so now when I look at what my interval of definition is, the interval of definition that works for both of them is the set of all xy values such that, and here's where we're going to get the either or, x is greater than 0 and y is greater than 0, or x is less than 0 and y is less than 0. Those are the only options there, okay? And so if we look back, we could say it says determine a region of the xy plane for which dy dx is equal to the square root of xy would have a unique solution whose graph passes through a point, x naught, y naught, in the region. So when you do your homework, if you're in WebAssign, it's going to ask you for a region. This set notation isn't working very well for that, but one region, so let's write out what the possible regions are. One region is x is greater than 0 and y is greater than 0. Another region is x is less than 0 and y is less than 0. I can't do intervals because there are two variables involved here. And if I start writing interval notation for either one of them, I lose the information of the variable, like which variable I'm talking about. So I have to use an equality notation here. But that's it. One or the other of these regions would work. And if we knew a particular initial value, we would be able to determine which region it is in. So let's just say we would want an initial value to be in one of these. If it is not, like for example, let's pretend that the initial value given is in the fourth quadrant. What that means is that I do not have a unique solution to that IVP, okay? I have the existence of a solution, I just don't have a solution to the IVP. And that's all that it means, okay? All right. And that is it for this section. There really isn't a whole lot to this whole section, right? We've got the finding parameters and determining the interval of definition. And then we have the existence and uniqueness. And so if you're struggling with any one of those, don't hesitate to reach out and get some help.